Okay, so for 1.6, we're going to talk about trig functions. So we're going to do like some review on trig functions. Now, there's a couple of things you need to remember about trig functions. Trig functions are nothing more than the, we're comparing the two sides or legs of a right triangle, and there's three sides to a triangle, and so there's a variety of combinations, right? I think there's like 3 combinations. So first, let's just kind of review real quick. If I have a right triangle, and we call this angle here theta, okay? Then the side across from that is what we call the opposite, and I'm just going to designate that with the letter O. And always the longest side of a right angle triangle across from the 90-degree angle is going to be the hypotenuse, okay? And then the remaining side is the adjacent. So when we want to compare those, our trig functions are nothing more than a comparison of 2 of the 3 sides. So, for example, sine of theta is nothing more than the opposite side length over the hypotenuse. Cosine of theta is equal to the adjacent over the hypotenuse. And tangent of theta is going to be the opposite over the adjacent. And normally when I teach this in pre-calculus, I tell the long story about chief. I think I just misspelled chief. Is that how you spell chief? I before E except after C? Yeah, I think so. SOHCAHTOA. And that's a great way to remember what means what. And so if you look at this carefully, sine, or so, the so portion, means that sine is the opposite over the hypotenuse, okay? Ka means that cosine, all this stuff here, means that cosine is the adjacent over the hypotenuse. And then lastly, toa, all this stuff here, just means that tangent of theta is the opposite over the adjacent, all right? And then we have the reciprocals of those functions. And so the reciprocals of those functions are simply going to be cosecant, which is going to be theta over cosecant of theta is actually the hypotenuse over the opposite, and then secant is going to be the hypotenuse over the adjacent, and then cotangent of theta is just going to be the adjacent over the opposite side length. Now, when we think about this, and I'm going to use my that was easy button, we could also think of this as, and let me do my that was easy button thing, in analytical geometry or trigonometry, specifically here in our calculus class, what we're going to do is we're going to focus on the graphing of trig functions and where those values come from and stuff. So we got to review kind of the unit circle just a little bit. And so let's pretend that that's a perfect circle where the center is on the origin. And this is my x-axis and this is my y-axis. Okay? And what I want to do is I want to develop some sort of relationship between the x and y value and the radius of the circle. So if I were to start from the terminal, not terminal, but from the initial position. So let's make this yellow line, this is my initial position. That's where I'm starting from every time. And remember, this is quadrant 1, right? This is quadrant 2. This is quadrant 3, and this over here is quadrant 4. So if I start that side and I'm going to swing around over here, so this is my initial position, initial. Yeah, I was spelling it right. What was I thinking? And so we call this the initial ray. And then I call this purple line the terminal ray. Cool thing happens. If I drop a vertical line from where this terminal ray intersects my circle, I have this point here, by the way. This point on the circle is represented by x comma y. That's an x comma y value. Well, the distance from here to here is the radius of the circle, right? And this is kind of like a 90-degree angle, and I can think of this right here as being my angle theta, right? Oh man, we got all kinds of good stuff going on. And so then how do I determine this side of the right angle triangle and this side? Well, to get to x comma y, I have to go over x units and go up y units. Okay? So with that being said, we can rewrite our trigonometric functions in terms of the radius and the x and y. All right? And so if I were to rewrite those trig functions in terms of x and y, what I would probably do is I would probably do something along these lines. I might say something like sine of theta, which is usually the opposite over the hypotenuse, can be written as y over r. Where cosine of theta could be written as the adjacent over the hypotenuse, but in this case it would be x over r. And then tangent of theta, and I gotta slide this up a little bit, zoom out. Tangent of theta would be y over x. And then our corresponding reciprocals, cosecant of theta, whoops, got a little happy there. Cosecant of theta would be equal to r over y. Secant of theta would be r over x, and then cotangent of theta would be x over y. Okay? And that's important. And so what we see is as we graph these functions, if I plug these into an equation, in other words, as theta rotates around the unit circle, these are what we call periodic functions. Because the values are trapped between x and y. And so your x and y values may change, but because they're stuck on the circle, they don't change much, right? This x value is going to be similar to this x value, but it'll be a negative x value, and y will be the same. And then if you come down here, your x value will pretty much be the same x value, but it'll be negative, and now your y value will be negative. And then when you get to this one, both your x and y values will be negative. So, but the numbers themselves will be the same for all of the same theta. So we call these periodic functions because the value of the function is based on kind of the circle, that terminal ray sweeping around, and so basically once you complete the circle, the pattern repeats itself. So what that means is that if I go to graph, let's say I wanted to graph the function of sine, if I take out, and I'll just freehand it real quick, if I wanted to graph the function of sine, where this is, we could do theta, and this is my y value, or however you want to do it. Basically what it's going to do is it's going to look like this. We're going to have one cycle, and then it starts to repeat itself, and the same thing coming back here. And so we call it periodic because it's a pattern that just keeps repeating itself, and it goes on and on and on and on and on. Okay, and this one goes on and on and on, and it's just it's a wave. In fact, that's why we call sine waves sine waves. It's based on the sine function. And so what good does it do us to have a periodic function? Well, what we can do is we see that the y values are similar. So if I say f of x is periodic, then f of x plus the period p is equal to f of x. Now this is kind of a little bit more fancy formal notation, but basically what I'm saying is let's assume that this is some point here, and let's assume that this is some value for x, and this is f of x sub 1, right? So we have an x term and then the y term, right? So we have x comma f of x, and then I travel exactly one period, okay? So now I'm going to have a different x value, right? But really that x value is just going to be the period. So what I'm going to say is that, let's write it a different way. If I say x sub 1 plus the period p, right? So the distance from here to here is the period, whatever that is. I'm going to get f of x plus p, which is equal to f of x. Now the formal notation might really throw you off, but really what I'm saying is that, all right, I've got this value here, this is like my x comma y. Okay? Because the function is periodic, it has a pattern that repeats itself, then if I go exactly one period over, I'll have a different value for x, but I'll still have the same y value. Does that make sense? Okay? And that's all they're trying to say. So the reason we use that is because we just spent a lot of time talking about functions and them having one-to-one relationships. And so if I did the horizontal test on this function, it would fail the one-to-one, it's not a one-to-one function. It would fail that horizontal line test. But I still want to do some I still want to do some calculus on this trig function. So what I need to do then is I need to figure out a way to accomplish some calculus stuff and be able to make those calculations. And so what we do is we notice that the y values from here to here are the same. And so usually what we end up doing is we're going to chunk off a piece. So we'll chunk off this piece and this piece. So we'll create a relative domain, and we'll only look at this behavior here. Or we can chunk off any piece that we want. We make our calculus calculations, and then because the pattern repeats itself, our rates of change and stuff with regards to the derivatives are going to be consistent no matter where we are on the graph. Okay? And so now let's look at example number 1. So example number 1 then, that was a lot just to lead up to example number 1. Example number 1 is simple. Kind of went a little bit too much in depth. We probably could have done example number 1 without all that. So what we want to do then is example number 1 says, look, we want to find the arc length of a sector, and so we'll use a little bit more formal, the arc length of, and it seems redundant, I probably shouldn't have written down arc length, they really wanted the length of an arc, but I always write down arc length, of an arc subtended on a circle okay, with a radius of 3 and a central angle of 2 pi over 3. And so there's a formula for that, and I always remember it because my college professor said standing room only. And so the arc length S is equal to the radius times theta. It's not really, and so let me draw a picture. So what they're saying is we've got this circle, okay? And if I make theta 2 pi over 3, and my radius is equal to 3 units, this is S. This is what we're trying to find, okay? This right here is what we're trying to find, is that length of that section or arc that's subtended on the circle. It's real simple. I'm going to plug in what I know. S is equal to the radius, which is 3, times 2 pi over 3. Here the 3's cancel and I get 2 pi. And that's pretty much the answer for example number 1. You might say, well, Mr. Adams, you went in a lot of detail for that one example. Well, that's okay. I'm going to do example number 2 in a second. But there's a couple of things I want to point out. That this angle has to be, for this formula, it has to be in radians. So it won't work if you plug in degrees. You have to convert that to radians. Okay? So moving on real quick to example number 2, which is a similar problem, but a little different. What they want us to do is they want us to determine if something, we need to figure out that cosine of theta is even, okay, and we'll talk about that, and that sine of theta is odd. And you say, well, what, that doesn't make any sense. Something's even, something's odd. What does it have to do with all this trig function stuff? Well, we know that they're even and that they're odd, and we know that's based on their graph, because remember, this is reflected across, it's symmetrical about the y-axis, right? So this has symmetry across the y-axis, right? And then odd functions they have symmetry across the origin. And we should remember that from our pre-calc days. And then another way that you can think of this is that cosine, if I take f of x, that should equal f of negative x, right? So this is for an even function. And that for an odd function, if I take f of x, that should equal the exact opposite of negative x. And so if I graph those, it'll make it very clear which function is even and which function is odd. But how do we do that? How do we do that with the trig functions? All right. So we're trying to find the relationship between circles, arc lengths, the radians, or the radius and theta. Okay. So to prove that, I could say something like this. I could say that cosine, right, of theta is equal to, oh wait, let's draw a picture so you guys can see what I'm talking about. And this is a sloppy copy here. So I have my unit circle here. Here's x, here's y, some angle theta. So that's theta, right? Where this is the point x comma y, right? And we said earlier that cosine of theta was equal to x over r, right? So here's our radius, this is our x value, this is our y value. And we said that that was equal to the adjacent over the hypotenuse, so it'd be x over r. Now, if I take cosine of theta, negative theta, that means I'm just going to swing theta around this way. The exact same distance for theta, but I would say that this is cosine of negative theta, right? Well, again, I'm going to have a right angle triangle. The x value doesn't change at all. The y value changes because it's a negative y, but cosine, we don't care about that, right? So, because in cosine, I'm going to have the distance from here to here, this is the adjacent, it's still x, and the radius doesn't change, so it's still r. So what I'm saying is that cosine of theta is x over r, and so is cosine of negative theta. So this is an even function. Okay? Now if I wanted to do the same thing with sine, if sine is odd, right? It said sine is odd, show that sine is odd. So if that's the case, sine of theta should equal the negative of sine of negative theta, right? If that's true. So let's look at the picture. Now this time I'm going to draw two separate pictures so it becomes very clear. I'm going to have my little circle here. My little circle here, this is x, this is y, this is y, this is x. Draw theta, this is theta here. My little point here, so this is the radius. From here to here is y, from here to here is x. Now if I'm going to go the same exact distance, but now I'm going to have a negative theta, so this is negative theta in there, then this point right here is still, wait a minute, this is negative y, and this is the radius, and this is still x. In other words, this distance here would be x comma, same y value, but it'd be the negative y value. So this point here is x comma y, and then if I swoop around the other way with a negative theta, a negative angle for theta, I've got x as my adjacent, which we know doesn't change. My radius doesn't change. The only thing that changes is my y value is negative. So if I say sine of negative theta, I'm going to have negative y over r, which is the same as sine of theta if I toss that negative value to the front, right? Or, if I wanted to write it the way that I had it before, if I take this whole thing and put a negative sign in the front, which would give me sine of theta, when I push this negative 1 through here, in other words, negative sine of negative theta is equal to the negative of negative y all over x, which is equal to y over x, which is equal to sine of positive theta.